should also keep in mind that quantum technologies are progressing, but so are classical technologies. The classical technology has not stopped. There's a lot of things going on in miniature. Some part of the power will matter in matter conjugation. When n is the number of trials or number of observations. If you have a quantum setting, this can be made into 1 over n. And that is a big advantage in lots of applications, and I give some kind of list where this kind of things have already been demonstrated. So various things, atomic clocks, they can become much better than what we have today as the world standards, already demonstrated at the laboratory scale. Now commercial scale will come very soon, and they have applications in particular in global positioning system, because the distances which we measure are nothing but the speed of light multiplied by the time. Speed of light is a constant. And so if you increase the precision of time, the resolution of distance goes up immediately. And the advantage is expected in all these things are orders of magnitude. So it is not just 5%, 10% kind of thing. It's a much bigger thing sitting there if you can make it. And you can measure all kinds of things. You can measure electromagnetic fields. Particularly good candidate are nitrogen vacancy centers in diamonds, which are sensitive magnetometers. And if you can build them, that are all these MRI scanners in medical diagnostic centers, they will become like mobile phones. Okay, everybody can have it. And certainly, well, that's a life-changing scenario. You can have different kind of impurities also stuck in diamond. They will do different things. You can have memory. You can basically control everything or measure everything to high precision, whether it is position, velocity, acceleration, gravitational field, electric field, magnetic field, all kind of things can be done. You can put it in networks. You can detect things underground by a sensor on the surface, because you can note the change in gravity which can be caused by this. And these are all at the scientific level very simple instruments. A lot of them are basically interferometers. And interferometers are objects which work on signals coming from two different paths. And if the properties are slightly different between two different paths, you will pick up whatever is the difference. How well we can make it? Well, there are different platforms also, including two-dimensional materials like graphene. You can shuffle between electromagnetic sensing and a mechanical sensing. There are transducers available. All kinds of things can be thought about, and these are all becoming, as I said, practical in some form or the other. The advantages go over orders of magnitudes, and what they will require in addition to the quantum sensor, lot of peripheral electronics, because it has to be taken from the quantum signal level to something which we can observe. So we are all always classical creatures. Everything which we can observe is ultimately classical, and what we do, we can always write it with a pen and a paper, which is almost completely classical objects. So even when we have quantum signals, you have to connect it all the way to classical level. We need amplifiers, we need all the electronics which goes with that, and design of those amplifiers and the instruments is also quite becoming sophisticated. The simple reason is that in the process of this amplification, the quantum signal should not get destroyed. That is not as simple as it appears. You require a lot of sophisticated techniques, and it requires a lot of research work in that particular direction as well. Okay, let me go to topics of algorithms. They are useful in many situations just heuristically. Even when you don't have rigorous proofs, if something works, it doesn't have to work all the time. If it works most of the time, we will be able to use it. And fantastic motivation for looking at it this way comes from biology. The whole nature has evolved not by deriving proofs and finding the best solution. For them, it is whatever works, we'll take it and then worry about whether it can be improved later on. That is the whole process of evolution, and many of the mathematical problems can be looked upon these things. These days, lots of these problems are put in the language of machine learning and neural networks. They are not rigorous methods, but you fiddle around, tune something and find that this works. Okay, go ahead and use it. No problem. We'll find the proof later. So with that attitude, lots of things are being explored, and some examples I have listed here are something called randomized algorithms, which are popular in classical scenario, and the randomization there gives a probabilistic distribution, some weights over various possibilities. What can be improved in the context that instead of having this probability, you can put amplitudes, and then the constraint will be now sum over all the amplitude square is equal to 1. The advantage which comes in this amplitude can not only be positive numbers or probabilities, but they can be negative also. And if you mix up some plus and some minus contributions, you have interference. And that is where the quantum dynamics comes in. How do you create interference and enhance your signal? Well, it's an open question. Things are being tried out, and we know that in some situations these things help. how well and how much are open problems, and people are working on quantifying it. Another scenario is what is called quantum safe cryptography. This is actually a classical problem, highly mathematical setup. You have to give rigorous statements and give all kind of proofs because it's a cryptographic situation. But the point here is to develop a classical code which can be implemented with our binary logic of 0 and 1. Ultimately, all the messages are nothing but sequences of zeros and ones. But it is a classical code which cannot be broken easily by quantum hackers. So that is the motivation. And we know that such situations exist. Even if quantum instruments come along in a few years, we know already that there will be problems which even the quantum computers, the best of them when they will get created, find it hard to solve. Classical problems which are difficult to solve on a quantum computer. These exist. Then the job of this quantum safe cryptography is to convert those problems into some kind of code. And if you succeed in doing that, then even when you have a quantum attacker, you don't care. You are reasonably sure. But this conversion of a mathematical structure into a practical code is a non-trivial job. The famous example is the RSA crypto system, which is being used a lot. The mathematical problem is quite simple. If you give a large number, you find it difficult to factorize. But take that statement and try to develop a whole cryptographic system on it and prove that all these things now will not be able to crack this particular code. That requires a lot of work, and unless these proofs are given, the paranoid people who deal with security will not buy those instruments. Okay. So you have to construct those proofs, and that requires a lot of work, even when you know that it's possible in theory. And the examples are lattice codes and learning with others. These are very good candidates which we know are not easy for a quantum computer to crack. The question is to convert this into a cryptographic system. And work is going on around the world because a lot of it is hidden behind curtains because it's defense and military stuff. So they will not tell you what all they have been able to do. The third object which I wanted to highlight are techniques based on wave dynamics. These are in some sense analog devices, and we have not paid enough attention to them in the digital revolution. But they have something which the digital stuff doesn't have, and that is the possibility to have interference. Wave that already has fluctuating signals, they go plus and minus, whatever it is. If you figure out how to nicely combine them into an interferometer, you will be able to make new kind of algorithms. And if you use classical waves, still the interference is possible. And what you may be able to achieve with that will be not as fragile as the quantum dynamics. So this is a question. I will come to some example, but it has lots of applications on defect detection, energy transfer, catalysis, which are all some underlying wave features which exist, and the question is how do you exploit it? And all these things require a good background in linear algebra, because ultimately the mathematics underlying all these things is nothing beyond linear algebra. You are adding and subtracting vectors and playing with matrix multiplications. If you have good control and you know how to combine those parts together, you will be able to figure out some new things about algorithms. So something about communications. Here a lot of emphasis is put on the security aspect, but I'm going to stay away from it. So there is a lot of new things in communications other than security. What is that? The main point is improving the signal to noise ratio. And this is something which we know already from the experience of astronomers, how they do it. They detect all kinds of signals from the sky and give us fantastic pictures of galaxies and universe, black holes, all kinds of things. How do they do it? You can't see it directly. Even if you look at it in a telescope, you won't be able to make it out. So the simple trick is actually observe the fact that if you have multiple copies of the same signal, the distinguishability improves. So if you have say two states, psi and phi, these are vectors. These are written in the quantum notation, but doesn't matter. What does distinguishability do? To calculate the overlap between the two vectors, simple language cosine theta. If they are parallel, you can't tell them apart, and if you are orthogonal, you will be confidently saying that these two things are different. So you want to make the overlap between different objects sufficiently small. And now if you have two copies, and these have to be coherent in the language of quantum theory, they have to have correlation, that what is there is identically present over here. Now you calculate the overlap, whatever between this and this is, it is cosine square theta. And cosine square theta is smaller than cosine theta. That makes the distinguishability improved. This is very simple to understand, and what the astronomers have done is exploit this simple fact to fantastic level. They don't have two copies, they have actually large number of copies. How do they get copies? Either by having what I call large baseline interferometric instruments, many instruments spread over different levels, or observe the same thing for a long time and take many snapshots. The important point is that in these multiple copies, you have to retain the correlations. That means the phase information is important. If you can relate the phases of these two, you do interferometry and you pick out the signal to very high accuracy. In space, it is easy to see, it just works like any parameters. But in time, what they do is essentially Fourier transform, the signal in time. It combines some multiple copies, picks out the phase, and what you get is a very sharp signal that improves your resolution or whatever else you are looking for. So this is a property which is available in communication. The important point is having a coherent structure. If you can do this, then you will be able to gain a lot. And there are lots of components which go with that. One of them is a random number generator. If the random numbers are based on truly quantum property, they will be much more random than any of our classical systems which can design, and there are many ways of doing this. So these are now getting built in, particularly we will soon have them part of our mobile phones because it is all connected with communications anyway. You want random numbers to get into your communications, well, you can do it with a camera. That's basically what it is. There are sources, detectors, particular application which is useful for medical field is imaging with entangled photons. Again, a question of signal to noise improvement, and if you are able to do that, the radiation dose in our whatever X-ray machines or whatever other medical imaging instruments will go down tremendously. If the signal to noise sensitivity is large, you reduce the intensity, no problem. And instruments will improve quite a lot. Same thing goes about internet. People have already started dreaming about it, though making these kind of repeaters is not that easy task. But there are ideas of how to deal with that, and then our internet experience will also change. Let me say a little bit about security, that this communication structure actually doesn't solve everything. One of them is the authentication problem, that if somebody is impersonating for somebody else, just getting the signal is not going to tell you anything about it. So all the what you call machinery about spying and bribing somebody, etc., those cannot be eliminated by quantum signal. That problem remains, and you are stuck with a login and password and OTP or whatever it is. That there is no other way to deal with those kind of stuff. And another thing is this communication rates will not match the classical rates. The quantum rates will be intrinsically slower. That is because the instruments have to go between the classical and the quantum region, something detected here, something which we want to see, and the range is larger. And the going back and forth, it just basically takes more times, and the communication rate is inverse of the so-called dead time from one signal level to another one, and that is going to be smaller. The intensity of the quantum signal is going to be much lower, single photon, because that's what you are dealing with, and that means it's very easy to jam. Jamming is nothing but a function of the intensity of the signal. You make the signal weak, it will disappear into your jamming background quite easily. So there are going to be limitations, okay, and that is what will decide the applications, where you are going to put it, where these things are not serious problems. You have to design it, you have to think about those kind of environments. So now a little bit about simulations. I don't know how I'm doing on time. These are basically a mimicry of lot of things which happen in nature. I'm talking about simulations, not a simulator. Simulator is still a little bit afterwards. So there are lots of materials which we see, the molecules in chemistry, biology, all kind of environment. They are buried inside complicated whatever solutions or some particular structure, and you want to understand them better. So first, just for the scientific, but little bit more that, okay, I want to design new molecules, okay. Then you will have to put together all the knowledge you have obtained and find something new. And the new molecules can have lots of applications, going from pharmaceuticals to fertilizers or some new materials which will become a very good sensor. You don't know. And here the simulations is something that offers you just a mimicry. So what really you end up doing, there is some system which is possible in nature. You make a kind of map of that system into your quantum hardware. It will be a reasonably accurate map. Okay, it doesn't have to be 100% faithful, but a reasonably accurate map. And then if you are able to do that, then you have to let the hardware evolve according to the rules of the dynamics which you program. And programmability is important because that's where you will put all the parameters and play around that. Suppose I change this, how the material is going to behave. Suppose I change that, how the material is going to behave. And then it becomes a design platform. And that is what is actually used in lots of applications, whether you want to make a sophisticated aeroplane, or whether you want to make a new kind of drug, or whether you want to fight against some kind of disease. You need this kind of programmability and capability to play around with some basic components. And that can be done at a quantum level, provided you are able to perform that map from this whatever molecule is to your quantum hardware. Then the quantum hardware will do the evolution for you, and you will observe the final results that come out. And that is a very practical approach. And actually it works both ways. If you have understood the laws very well, then your mimicry will be very good, and you will get something out as a useful outcome. But suppose you are not able to get anything properly by this mimicry, and then that will tell you that you have not understood your laws properly. So that is a motivation for a scientist, that this is the material I have not understood properly. There must be some new dynamics, some new property buried inside it. Find those new laws of nature, whatever they may be. So it cuts both ways. If you have a very good understanding, where you can find its consequences. If you can't find good imitation, that means you have not understood the laws properly. And this is a new field which is going to grow, result of our being able to make quantum devices, and that has a lot of scope. And as a matter of fact, this is one of the main motivation for scientists about what to look forward to. We are not going to just look at solutions to our existing problems. We will probably find some new things to tackle which we don't yet even know about. And that will be the real, what you call, change or disruption in the way of our own thinking that can come about as a result of this particular technology. And the underlying feature of all this kind of simulation is what is known as a quantum parallelism. That we are doing actually this kind of things in our existing computers, but it is most of the time trial and error. You explore all possibilities one by one and scan through them to find a best choice. What quantum parallelism offers, that all of these things can be done simultaneously, like a parallel computer, but with the important advantage that you don't require parallel hardware. What you use is superposition, and that means you do multiple evolutions in the same device in one shot. And if you are clever enough, you will be able to figure out from those multiple parallel threads what is good and what is bad. That is where all the sophistications of our quantum theory knowledge will go in. And examples are a lot of them. I will not go through the list. So as a result, keep this thing in the mind. This is a sort of my advice to all the people who want to jump into this particular field, that you have to go after tough problems. Okay? It is not just a superficial strategy that I will write this particular code and it will do a great job. You need a good knowledge of quantum physics to achieve something non-trivial. That is the first step. And then keep in mind always that whatever comes out are going to be special purpose systems, which will work well in stable and protected environments. They are not going to replace everything which is around, though ultimately you can say that everything is made up of quantum materials. We are not going to do that. And here are some specific situations. Every quantum system will need a design platform. It's advantageous for us to first design it in a software, then try to make the hardware for it. This is just a question of saving resources. You have a lot more freedom to play around with parameters when you are dealing with software than you are trying to fabricate something. You have to make all the elementary components well. How to good? It is always necessary. There have to be what you call objects with high quality. Error rate has to be brought down below a sufficient tolerant level, and then only think about how to put them together and see whether they work. And from this point of view, these elementary components will become very easy to integrate into these high precision sensors and imaging devices. These are not large devices. They have a small number of sensitive components, and if you have been able to create those components with good fidelity, you'll be able to immediately convert them into good sensors as well. And that is a stuff which I can say on the theory side. This is the experimental side. The theory side, I already mentioned some of them. These are quantum-inspired algorithms, quantum-safe cryptography, simulations of molecules and materials. They can be done, and you have to again pick from this what you can do easily with our existing computers. Okay. Again, don't have the capability to do everything which you see in news reports, but you can pick and choose. Yeah, so now just some very simple example, which is thought-provoking, and this is something which I mentioned as a consequence of wave dynamics. So I will give you an illustration. It was a Grover's algorithm for database search, and what it shows that with one binary query, yes or no answer, how many objects can you distinguish? The Boolean gives the number as 2, but the quantum or even wave answer is. So how do you distinguish 4 objects with a single binary query? This is the illustration. You start with a distribution which is unbiased. All of 4 possibilities equally likely. And then you ask the binary question, but you use it in a clever manner. What are you going to do with that binary answer? You change the sign of the amplitude which responds to the binary question. In this picture, it is the first one. This is something where the wave and the interference part has gone in. You are able to change the sign of the amplitude. And that is enough. Don't do anything more. Any wave, once it is perturbed, here everything is equal, it is nice and stationary. You give it a kick, a binary kick. It will always oscillate about its average position. That's the nature of waves. So what is the average number? I have normalized this thing to the square of all the amplitude equal to 1. That is a standard convention. But after this, 3 amplitudes are plus half, one of them is minus half. The average is a quarter. Now let it oscillate, and let it oscillate by half a period. So it is on one side, half a period, it will go equal distance on the opposite side. So the numbers which are all plus half, after that half oscillation, fall to 0. And this was minus half, which is 3/4 below the average, add 3/4 on top of it, it becomes 1. So after half an oscillation, you have this distribution. And you just say stop. And if you now make an observation here, you will identify which particular amplitude has flipped inside. And the detection is, in this example, 100% faithful. What you want has 100% fidelity, what you don't want is 0. So one binary question, wave dynamics, solves the problem that you get 1 out of the 4 items in database with guarantee. And now you think about it, this algorithm was written down by Grover in the context of quantum computing. What is quantum in this? You can actually do it as a tabletop experiment. You need 4 oscillators and the capability to reflect one of them, which is very easily done. You hit it with a wall to change its sign of the velocity. So that's it. It was a great fun for me to make it as a what you call high school science project for my son. And it won prizes. All those are other details, but this is something which can be demonstrated, and there are a lot of this kind of wave realizations, which are some things which have not been explored. And it's worthwhile to think about those directions as well, not just label everything quantum and then forget about what else is available with the same mathematics. Mathematics is not different. But you learn new tricks and you have to figure out where else they can be applied. And here there is another interesting story which I did work on from some example. Do we know of a database which works in selection of 1 in 4 as a sequence? And the answer is yes, we all have it. It is in our genes. Did that anything to do with this kind of analysis? But as I said, nature doesn't care. It could have picked it up, this elementary bacteria or whoever developed the genetic language, by trial and error. And the point is that this is an optimal solution to the problem. That's the important part. This is the best solution, you cannot improve on it. And in nature, that is very convenient. The best solution is found. It will compete and win against everything else, and you have no competitor. That is indeed true for the genetic language, where there could be competitors. Even our binary language is perfectly okay. It will code all the information, but somehow nature decided that no, that was not good enough. Why, we don't understand fully, but this is the kind of situation which has perfect map between what we are learning in quantum physics and what we observe in nature. That's a different direction, but something to think about. And I have a video of this 4 oscillators. I can maybe show you at another time if at the end of the talk or somewhere else, no problem. Very simple. And now I come to the last part, which concerns simulators. This is something which is part of this particular workshop. And as I said, they are basically some modeling platform which use less resources and give you the desired answer. And in this particular case, we don't have a quantum computer. So we make a cheap version of it, which is the simulator. And as long as you are working on the cloud, you submit a job and answer comes back. You have no idea whether the real computer is sitting on the other side or just a simulator. As long as you get the answer in your required time, you are happy. So this is a kind of simulator which I sat down with my students to develop. The purpose was to make things for small systems, make it so simple that everybody can use it. So we made it so that anybody can download on the laptop and run, no problem. Of course, when you say that it will run very faithfully and very quickly on a laptop, there's a limitation on size. But we discovered that up to some 10 qubits or so, everybody could run it on the laptop, and the students were very happy. They were just taking this program, download it on laptop, and explore it at their own convenience. It's like giving a mobile in everybody's hand and let them use in whichever way you want. But this is the best thing to do when your focus is education. Not everybody is going to make what you call use of this kind of things for doing research. But for popularizing the system, it's great. So this is the drive behind the simulators, and actually it was nice that MIT picked it up and put it as a educational platform for the whole country. It's all open source, free of cost, whatever it is. And we expect good things to come out. So what I did was actually some 3 years back and made library and put it on GitHub. And at present, I'm working on the second version. So it will come out in a few months' time. The history was that the first version was actually just a summer project students with a bunch of undergraduates. So that's all that was required. No sophisticated resources of any kind. We sat down for the summer project, 3 months, we had the software library available for everyone. And the new version is going on right now. 3 months, it will be out. Okay. Doesn't require too much what you call resources, but requires some amount of understanding of quantum physics, what is actually going on. And the purpose is to design simulators for all kind of devices that you want to make. So the first generation was done on the platform by IBM, which was QSCIT, simulates a superconducting transmon-based quantum computer. The new version will have other platforms as well. Photonics, for example, requires different kind of operations, but again, some kind of output which will have quantum signal in it, and we can reorient various things so that it will give the output in that particular format, no problem. So, and it will others include other systems like ion traps. Ion traps use a different platform, different kind of operations, but you'll be able to predict what will come out, and then it will be the choice of the user. I want to run it for superconducting device or ion trap or photonics. We will be able to see whatever comes on. And the important point is that while doing this thing, we need 2 criteria, verification and validation. So the words have some specific meanings. Verification means that you design with certain input specifications. Whatever you have designed agrees with those specifications or not. And validation is at the other end. The target performance, whether it is within your desired range or not. And every device needs this. You need to specify the input components, how well they are able to be made, and you want to specify the output, how good your output is, up to what accuracy. And simulators are all geared so that you can address these 2 particular questions. And for that, you need to understand all the sources of noise, fluctuations, errors which go into the system. Because that is where the questions of verification and validations is important. The real world is never going to be perfect. There are going to be all kinds of disturbances, and you have to see how good or bad your system is in presence of those disturbances. So Once you have done that, the purpose is expanded. It's not just educational, but it becomes a design platform. Anything you want to make, now you can play around on this design platform, and we are actually targeting that particular aspect in the future developments of the simulator. We want to make it useful for various kind of designs. And keep in mind that all the computers, people talk about all kinds of applications. But what is the first application which they always do? That a computer is always used. The first step is to design a better computer. Not for some great application, but you have done something, you want to improve it. The computers in a quantum scenario are no different. First target is to make those computers better. And that is where all the knowledge of design and various criteria, how to tune this parameter, that parameter, etc. Goes in. And yeah, here I wrote down some practical criteria. You should be aware of what are the interactions with the environment which can occur for any hardware component, what are the materials involved, what is the geometry of connectivity of various components. They all interact, and many times, as luck shows, that the naive estimates of error are generally too pessimistic. And the computer theorists, they give some bounds, the order epsilon, whatever it is. And those things are too pessimistic because they want guarantee that it will always work. What happens in practice is not only the signal gets spoiled, but the error also decays. The signal can decay, the error can also decay. I mean, there is nothing great about error as far as some physical property is concerned. So even if the error enters at some stage, it may have decayed, and your instrument will do a better job than what you expected. And this kind of features come out of the simulators. You will mathematically not be able to derive it very precisely, but in the simulators you see that disturbance came and it disappeared, and then your answer looks, well, good enough. And the reason behind this kind of thing is a fundamental property in physics that everything, all interaction, whether it is signal or whether it is noise, is local. You have disturbance, but it will be in this particular region of space and time. What happens over there has no relation to what happens over here. This is called locality in physics. And because of that, the disturbances actually decorrelate and decay at a faster rate than naively what you would expect, and you take advantage of that particular fact in the simulators which you program. And yeah, whatever we included in our simulator are this particular aspects. The initial state will have fluctuations, typically due to thermal effects. And whatever you say, the initial register is all zero, it's not necessarily all zero. Sometimes zero and sometimes fluctuate into one. This kind of things happen, and you have to estimate what is the error coming from that. All the dynamics of logic gates, they may be imperfect because there are some parameters, particularly in the quantum space. There are all some electromagnetic signals, whether it is by fields or lasers or whatever else you use. They have some intensity, some width, and those things are not exact. There will be some plus or minus inside there. And if you apply that, the logic gate also will be plus or minus something that you have to include that error. Every time there is a hardware, there is an environment, and all kinds of effect coming from the environment. They are parameterized in terms of decay and decoherence. The important part is that these things are present even when you are not doing anything. The data is supposed to sit idle in memory, but these things are still going on. So the memory gets spoiled. In our classical system, we have nice codes to protect them, but in quantum system, it is more delicate. And even measurements are not perfect. You think that you observed something, or even worse situation, you put a detector and the signal is lost. You have to account for that. Whatever it is, some imperfection, but you include that also as a parameter, and at the end, you will get an output which is not deterministic but probabilistic. It works sometimes, it doesn't work sometimes, and even when you have an answer, it is plus or minus something compared to the true answer. And the job of the simulator is to give you all those plus or minus quantities. So you run it with a bunch of parameters which you can tune, and you can vary that the error rate from 0 to some non-zero value, how the answer deteriorates. And then you decide that, okay, I want a good accuracy, the error parameter should be within this particular bound. And if you do that, you now have a design statement. And that is what we are after in any way in this particular game. So we did that for all these errors, and this is a reference. It's available on this public archive. It's a published paper, but the archive is free, everybody to see. So you can find it over there and figure out all the statements written inside there. As I said, you will require some amount of knowledge of quantum physics, because the paper is there, but you have to understand each and every statement. That's the way I have written it. So if you ignore some statement, then you are lost. You have to understand each and everything to be able to figure out what has gone on. And it's available on the IBM platform, the mathematical structure which we used, and this is from quantum physics. It's a density matrix representation. And this is the price that we need to pay to be able to simulate all the errors. So there are not many theorems in quantum physics which tells you that this is a correct description, but the price you pay is the standard definition which goes into evolution according to Schrödinger's equation is that as a vector, and you multiply it with a unitary evolution. Here, instead of a vector, you end up dealing with a matrix of the same dimension, but the result is instead of having n components, you will have n square components. And that slows down the performance. It's basically squaring up of the degrees of freedom, but that is absolutely necessary. And it's again a theorem that if you have an n component quantum system, it can be perturbed in n different ways by the environment. You can prove it, and you can show that it is enough that n environmental disturbances will account for everything which can happen. You don't need more than n. But once you have these two factors, n component system, another n component from the environment, and you want arbitrary interaction between them, you end up with n square. There is nothing less than that, and that n square is coded into this matrix. The result is that instead of having a binary number like 2 raised to n for an n component vector, you will have 4 raised to n variables to deal with in the simulator, and the result is that with a fixed amount of memory or resources in the computer, the number of qubits that you can handle becomes half. So if in the vector notation you can handle n qubits, density matrix with the same space and memory, you will be able to handle n over 2 qubits. And that is essentially the price we had to pay. What we got at the end of it, that 10 qubits and of the order of 100 operations can be run in a few minutes on a laptop. And this is what the students were very happy to play with. C-DAC took over this library which we have constructed and added more things to it. Nice user interface, a parallelization using a graphics processor which is available on bigger system, etc. So these numbers go up with the same amount of time, but a more powerful system. You can go up to say about 15 qubits and 1000 workstation, and this has been implemented on the Param computers, which C-DAC has put on this qctoolkit.in platform. So that is the status of what is available right now. And as I said, in 3 months' time, we will have a new thing to announce. This first one we announced on 15th August. So let's see what happens on this coming 15th August. Thank you. Yeah, I had something on running the simulator. I will just leave it on the screen. I have talked enough. But basically, to use this, you need how to write codes in Python and use of Jupyter notebooks. The graphical interface is available where you can click and point on various things. And all kind of enhancement are available. We use the NumPy package, but with different platforms, you can use more sophisticated libraries, which will improve the performance. C-DAC has added some of those things into the simulator.